Hi, I'm Tom Sandry, Director of Technical Support here at ProTech Equipment Resources, and today I'd like to take you through the Megger BITE Model 2P. BITE stands for Battery Impedance Test Equipment, and the instrument that we're going to be demonstrating today is designed to test the state of health of standby battery systems, whether they're flooded, sealed, NiCad, or lead acid. The system basically consists of two pieces. The main unit, which I'll refer to as the BITE transmitter, and then you can see in the handle here a two-part receiver gun, which will actually be used to probe along the terminals of the battery jars. Now, the way the system operates is the BITE 2P will actually get connected in parallel across the battery string that we're going to test. So, the unit comes complete with a set of current leads, which we'll just unwrap here. Plugging one side into the transmitter. And then plugging the opposite side across the battery string that we intend to test, similar to the way I have it drawn on the board here. So we'll take the red lead, connect it onto the positive post of cell number 1, and then we'll take the black lead and we'll connect it onto the negative post of the terminating or final cell, as shown here. Now notice that the BITE 2P is in parallel across the battery string, and then the battery charger is also in parallel across the battery string. Now, the way the BITE product operates or conducts its test is the transmitter is going to inject an AC current into the battery string. Now, the combined impedance and combined strap resistances of the battery string should be relatively small in overall value compared to that of the load. Therefore, when we inject the AC current, the vast magnitude of current is going to flow through the battery string, being that this is the lower impedance path as compared to the load. So all current should flow through the battery string back to the transmitter with no carryover into the load circuit. Now, that means that the battery bank can be tested while connected to the charger and to the load and never have to be taken offline, which is one of the attractive features of doing the impedance test. At this stage, I'm going to go ahead and prepare my measurement receivers. Now, the measurement receiver can be considered to be quite simply a multimeter, if you will. It has the capability of measuring DC voltage. It has the capability of measuring AC voltage and AC current, as well as resistance. At the bottom end of the gun, you'll see connections to go ahead and connect your other receiver. This plugs directly in. The kit also comes with a current reading CT. Just set these down momentarily. The CT will also plug into the bottom end of the gun. And the CT will get connected anywhere within this loop circuit. So most convenient would be connecting it across an inter-tier cable. Now, the way this technology works is the bike transmitter is injecting an AC current. The bike receiver is going to actually measure that current value. The potential guns are then going to measure the AC voltage drop across the cell. By measuring the current and measuring the AC potential drop through Ohm's law, we then calculate the internal impedance of the cell. And that's the value that we're looking for trending. Now, first step is we will go ahead and turn on the receiver gun. And it's going to ask us a few questions. First, do we have a bar graph wand? The bar graph wand is convenient if you want to enter in header information, location information. Since there is no keyboard on here, Megger does sell a bar graph reader as an accessory. Since we are not using one, we'll just push the N for no. The next question is, do we have a battery baseline value? Now, a baseline would be, what impedance would I expect to see on these battery cells? Now, a baseline, I might be able to come up with that value by contacting Megger. I might be able to come up with that value through my own history of testing of battery cells. And in some situations, I may get that value through the manufacturer. Now, we could enter it into the byte receiver. My preference is, which we will demonstrate a little bit later, I'll use the baseline information after I download it into the report generating software, and I'll let the comparisons to baseline be performed in the software rather than in the receiver. So I'm going to say no to the baseline. Do we have a split strap situation? In some battery systems, due to the sheer size and the amount of amperage that they would discharge at, several times we have cabling in parallel with one another, making our connections from jar to jar. Now, that may be where the clamp, the jaw opening is too small to get it across the whole bundle, so I only connect across half of the bundle, in this case a split strap. In which case I'm only going to be reading half of the true current flowing through. The byte receiver is equipped to deal with that situation by simply notifying that we're dealing with a split strap. Since I'm not dealing with a split strap, I'm going to say no. Do I want to save these settings for the test that I'm about to perform? I'm going to say yes. And now it prompts me and it says connect the CT. I have the CT connected and I'm measuring 0 amperage. Now, the transmitter is turned off at this point. So if I were to measure any AC amperage, that amperage would be a byproduct of the efficiency of my charger. And in essence, what I would be measuring here would be any potential ripple current. Ripple current is a byproduct of an inefficient charger. I'm measuring 0. I've got a very good charger. Now, when I push the trigger will merely save that measurement to the internal memory of the receiver. You hear the beep, I captured the measurement. Now it's going to say connect and power up the transmitter. Well, I've already got my transmitter connected. The next step will be to power it up. So I turn it on. And I'm going to wait for the current ready lamp to illuminate. So I push the current button. It is now charging the internal capacitors. When the transmitter is actually transmitting, we will see the current ready lamp come on. And we are putting out 11 amps of AC current. Now if I look on the receiver, the actual current flowing through the battery string with all of the combined losses is 10.4 amps. That is my test current. I push the trigger and I capture the value. Now it's prompting me to go to jar number 1 and or cell number 1, and it will then take a DC voltage measurement. This is going to be the charge voltage, and then it is also going to tell me the internal impedance. So to make the measurement, we merely go across the battery, trigger the gun, and capture the measurement. So as you see, I had 15.44 volts and 6.59 milliohms of impedance. It is now asking me to take the strap measurement. So I will now go across the interconnecting strap going from jar 1 to jar 2. I'll capture that value. And now it prompts me to move on to jar number 2. And I will continue through the test in this manner, capturing the DC voltage, internal cell impedance, followed by interconnecting strap resistance. As you can see, the test moves rather quickly. Now, on the very last one, you'll notice that you'll always have an uneven count of cells versus straps. So, for the very last measurement, I'm going to fake a strap connection by simply connecting the tips of my gun together and recording a final strap value. When I have finished the entire battery string, in order to review the data, I will simply disconnect my second gun probe, and I will connect the communication cable supplied in the kit. Now, if you watch the screen, as soon as the communication cable is plugged in, the byte receiver recognizes that it now has a connection to a communication cable, and it is going to ask me if I want to transmit or download my data. So I'm going to now take my communication cable and I'm going to plug it into the printer port on the byte 2-piece transmitter. It's asking me, do I want to transmit data? I'm going to say yes. It's going to ask if my test is complete. If I say yes, that my test is complete, the file is going to be saved and locked. That means you will not be able to come back and edit data. So, if you've just got done testing 120 cells, you may want to say no to this, print the data, do a review, make sure that you've captured reasonable data, that you didn't maybe inadvertently miss a cell or miss a strap, because once you say yes to test complete, you will not be able to go back and edit. If I say no, I can still print the data and review it, but it will allow me to go back and remeasure certain values if I need to correct them. For right now, I'm going to say yes, my test is complete. And then it says, are you sure? Are you sure you want to lock this file? I'm going to say yes. Now, it gives me the choice whether I want to download it to a PC or computer, or do I want to download it to the internal printer in the byte 2. I'm going to say download it to the printer. Do I want to do all the tests or just a selected test? I'm going to say just the selected test. Now, just so happens I only have one test stored in here. But if I had 15, 20 different tests in here, I could scroll to the particular test that I want to download. Once I get to the one that I want, I simply say accept. Printing is in process. And what I show is cells 1 through 4. In this case, they're actually 12-volt jars. It shows me my individual impedances of approximately 6.5. Notice also that my ripple current that I captured earlier was at 0. The test current flowing through was at 10.4 amps. The minimum impedance of the cells was 6.272. The maximum impedance registered was 6.587, and based on 4 jars, my average impedance then became 6.4. I also have my strap resistances. Now notice my first strap resistance very low. My second strap of 1.081 is much higher, but consider it's a much longer piece of cabling going from one jar to the other. My voltages ranged from 15.4 to about 14.6 on the low end. My deviation chart, and here's where I can compare each jar against the others to see if I have a potentially weak jar. I'm showing this as a plus or minus deviation from average. So a cell that's deviating toward the positive may be going toward an open circuit state. A jar or cell that's deviating toward the negative may be going toward a short circuit state. What I'm looking for is an ideal grouping where my plus or minus deviation is within approximately plus or minus 10%. If I either get a plus or minus deviation in and around plus or minus 15%, I'm going to flag that as a warning. I'm going to do a little bit further investigation of that particular jar or that particular cell to see why it's deviating so widely outside the average. If I see a deviation of approximately 20% or greater when dealing with lead-acid batteries, I'm going to flag that as a potentially failed cell, and again I'm going to investigate deeper. I may even choose to jumper that particular cell or jar out of the bank and to conduct a single cell or single jar load test on it to try to determine if it's fit to keep in the bank. And that has been our brief presentation and demonstration of the Megger battery impedance tester model Byte 2P. Thank you for your attention.